Hello, welcome to the FRQ of the day. So today we're going to be looking at the 2015 number 4. So I encourage you to give this one a try. So I'm going to read it, and then if you want to pause the video and see if you can do this, then we will talk about the answer. So the 2015 number 4 says, a researcher conducted a medical study to investigate whether taking low-dose aspirin reduces the chance of developing colon cancer. As a part of the study, 1,000 adult volunteers were randomly assigned to one of two groups. Half of the volunteers were assigned to the experimental group that took a low-dose aspirin each day, and the other half were assigned to the control group that took a placebo each day. At the end of 6 years, 15 of the people who took the low-dose aspirin had developed colon cancer, and 26 of the people who took the placebo had developed colon cancer. At the significance level of alpha is equal to 0.05, do the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer among all people similar to those, or similar to the volunteers? Okay, if you want to pause the video and give that a try, that would be great. Okay, so this one right here is a pretty stock two-proportion z-test, and so you're asked, in essence, is there statistically significant evidence of a difference? And that means do a test. That means get a p-value and do the THAME acronym. And so each part of the THAME acronym is a part of the grading rubric, just a small part of which is getting the actual p-value, by the way. So anyway, so let's talk about how you would do this. And so so the first thing you would recognize, now, by the way, so so the whole premise of this is you had 1,000 people, 500 were randomly assigned to take aspirin. So you've got, for the aspirin, so you had 500 aspirin, how do you spell aspirin? Okay, yeah. So the aspirin people, all right, so you had 500 of them take the aspirin, and 15 of the 500 developed colon cancer. All right, and so that would be 3%. That'd be 0.03. That'd be 0.03. Okay, and then they took the placebo. And so that would be, and so that's 26 out of 500. And so that is 0.052. And so a higher percentage that took the placebo developed colon cancer. But the premise of a hypothesis test is this, and in this setting, is this difference, is it so different that it's not plausible to happen because of sampling variability? Or is this a statistically significant difference? And so that's the premise of what we're doing. And so we're dealing with proportions here. And so its proportion is z. I mean, there's two situations that you got to be aware of this year, and that is proportions, doing z or t intervals, and tests and means, in which case you do t intervals and t-tests. So proportions you do z's, with means you do t's. Okay, so this is proportion. So we're gonna do z. And so the first thing you have to do is you have to state what you're doing, and this is a two-proportion z-test. So that is the t of THAME. That is the type of inference. You have to say what you're doing, or you could write the formula down. Either one of those would count for naming it, because all these inferences have a unique formula. But the easiest thing to do is just write that down. I wrote the formula down too, but anyway. And so then you have your hypotheses. And in this two-proportion testing, it's always that the two proportions are equal, or sometimes you'll see that the difference is equal to 0. And then it says up in the problem, do we have evidence that the low-dose aspirin would reduce the chance of developing colon cancer? So that's telling you less than. Okay, that's telling you less than. And so, of course, you have to define, anytime you write a variable, you have to define what they are. And so, and then P sub A is the proportion of all people like these. Okay, with these people were not randomly selected. We're going to talk about that in a second. Who would develop colon cancer after taking aspirin each day for 6 years. And then this should be a P, not a B. So this is a P for placebo, like that. And so that's the proportion for placebo. It's actually the tense of your verb is important here. Don't use past tense, because if you use past tense, then it makes it seem like you're talking about the sample. So you want to go with future tense in this particular problem. Who would develop cancer? All right. And so that is the H of your THAME, your hypotheses, and that's how you do that. And then you do your sinning, your conditions or your assumptions. Now, first of all, it does not say they were randomly selected. It says they were adult volunteers. So you have to clearly state that we can only generalize about people like these. Okay, but they were randomly assigned. It says clearly that they were randomly assigned. So your random condition is met, but don't say random sample. You have to say randomly assigned or randomly allocated. Okay, don't say SRS. We didn't have an SRS. So it says the 1,000 volunteers were randomly assigned. So random condition is met. Good Lord, I didn't write it down. I mean, I wrote it up here and down there, so I'd have been okay. So 4 people like these. 4 people like these. I can't believe that I didn't write that down after I just preached to you to do that. So, but like I said, I would have gotten away with it, I do believe, because I wrote it up here and I wrote it in the conclusion as well. All right. So now technically, and so this, and look, so the other thing is your N times P in any, okay, wait. Now the I, the independence, where your population size has at least 10 times your sample size. You don't have to check that here. And the reason is we have not had sampling without replacement from a larger population because we took volunteers. Okay, so you don't have to have that. If you did check that and say, oh, there must be at least 10,000 people like these, it wouldn't be counted wrong. Okay, but so you don't have to check that here. So if you on a problem like this, you may look at an answer and it may have that, and so I don't want you to be confused about that. But these are the only 2 in the rubric that you had to check. Your N times P and your N times 1 minus P have to be greater than 10. So then you'd say normality is met. Now the result of that is the sampling distribution of all possible differences is approximately normal. So that's the way that would appear in a multiple choice problem. But anyway, you'll notice in a test we use the pooled p-hat. The pooled p-hat, which means we just combine our p-hat for the aspirin and the p-hat for the placebo, and to get that. The reason we do that is that we do the whole hypothesis test assuming the null is true. The whole premise of this is if we assume the null is true, what's the probability we're going to get sample values as different as we did? That's the premise of this. And so if you combine the 2 samples, it creates a larger sample size at essence, which creates a more accurate estimate. We don't do that when we do confidence intervals. So I use the pooled p-hat to go, N times P and N times 1 minus P. Now, if you just did it with the 2 samples like you did in the interval, in other words, your N times P was 15 and your N times 1 minus P was like 485, and your N times P for the placebo is 26 and N times 1 minus P was like 474 or something, that would be fine, okay? That would be fine, but you have to show N times P and N times 1 minus P are greater than or equal to 10. And I only did it twice here because both our sample sizes were the same size. Okay, so there's your conditions. All right, now your mechanics. And I went ahead and did the formula. Okay, so the formula, which you don't have to do, but you do need to be able to recognize that formula. Okay, it's really unlikely it'd be in a free response problem, especially in this year's test, but I went ahead and did it anyway. So the formula for this, for your test stat, so on your formula sheet, standardized test statistic minus parameter over the standard error. Well, our statistic is actually 2 things. It's actually those things. Okay, and our parameter is actually that they're the same. So our parameters are 0. All right, so there's our difference in statistics. And then the standard error of the statistic, that guy is over here. So the standard error of the statistic, you go here for proportions. And so that is it. That's the deal where for intervals, if you're doing an interval of a difference of 2 proportions, but when we assume p sub 1 is equal to p sub 2, which we're sort of doing that when we do a test, we're assuming the null hypothesis is true, then we use this formula here. We use that formula where, and there's your pooled p-hat. P-hat is the sum of your successes over the sum of your sample sizes. And so that is what I did here. That is that formula. And so there's your test statistic. And given your test statistic, the way you find the p-value is use normal CDF with a mean of 0, standard deviation of 1. And I went less than here. I went from negative infinity to that because my alternative was less than. All right, so you go in the direction of your alternative. If it was 2-sided, you would go outside of that. I would have multiplied this by 2 if it was 2-sided, if it was not equal to. And if it was greater than, I would go from that to infinity. But, all right, so that is sort of creating the p-value by hand. But I want to show you how to use your calculator, which is certainly the quickest way of doing this on a test. You do need to understand mechanics like that, but I wanted to show you this. And so our inference we have here, we hit the stat button, and then go to test, and then go to the 2 proportion z-test. two proportion z-test, and we hit enter. And so our first, so we have, it's 15 out of 500. So 15 out of 500, that's my first sample. Those have to be integers, of course. And then the next one is 26 out of 500. So this would be 26 out of 500, like that. So the alternative is less than. And then calculate is boom. And so the only two numbers you have to write down with z are this, or there's your z-test statistic and there's your p-value, and call it a p-value, don't call it p. Okay, call it a p-value. And so there you go. And so that's how you do that. Of course, if it was a t-test, you'd have to write down the degrees of freedom as well. But anyway, okay, and so we've got our p-value, and so then we'll do our conclusion with our p-value. These p-values below 0.05, so I reject the null. There is convincing evidence that, and then you have to restate the alternative in context. And I hate the fact that you have to state what p sub a and p sub p are twice, but it's not out of my control. So you have convincing evidence that, and then you restate this in context. Restate that in context. We have convincing evidence that the proportion of people like these who would develop colon cancer after taking aspirin each day for 6 years is less than the similar proportion than those for a placebo. And that's it. That's how you do a two proportion z-test. And one other thing that I think is a really decent chance they're going to ask you this year is, okay, this of course is drawing a conclusion with a p-value. There's also the concept of interpreting the p-value. And if you're asked to interpret the p-value, you would, in other words, to interpret a p-value is to describe it as a probability, which is what the p stands for, a probability. It is the probability of getting sample values this unusual, assuming the null is true. So if we were interpreting this in context, we would say, if it is true, given that the proportion of people like these who would take aspirin that develop colon cancer is equal to the proportion that take the placebo that would develop colon cancer. In other words, the drug does not work, okay, or the aspirin does not work. Given that's true, the probabilities we would get sample values this different is 0.0397. So that is interpreting a p-value in context. Okay, that's it for today. Thanks for stopping by. I hope you have just a wonderful day, and I look forward to seeing y'all again.